Welcome back to my favorite people. How are you? And pretty sure some of you are gonna say that I'm struggling with nucleophilic substitution reaction or SN2 reactions. I have to say this. This chapter is gonna take you some time actually to understand it. It will take some time to click technically. So have some mercy on yourself. And I will say this. How about this? Practice more and more examples so then you get used to the nucleophilicity versus basicity, and what's the meaning of, for example, SN2 or SN1, E1 or E2 reactions. You have to keep practicing more and more example. And again, if you are struggling with a concept, you need more help, you need me to practice some concept with you, please shoot me an email or let's meet in person or maybe online and Zoom, and I will be happy to practice more example with you. Okay, so there is no reason not to reach me. Please shoot me an email or like stop my office. Let's have a chat about it. Okay, so here we have an alkyl halide. We're going to treat it with a strong base, and the strong base here, instead of doing substitution reaction, it will do technically a hydrogen abstraction. It will take hydrogen from system, but from which carbon? And it will go after the beta carbon. And what was the alpha carbon? The alpha carbon is the carbon that holding the halide. So we have a carbon attached to another carbon, and let's call this one alpha. This one is beta. Okay, the alpha, it has X, whatever is the halide or the living group, and then I have hydrogen on the beta carbon. So we have hydrogen on the beta carbon. Our base is with a lone pair is going to go after this hydrogen, and then it will attack that hydrogen. Now hydrogen, it has 2 electrons, and hydrogen is going to share those 2 electrons or give those 2 electrons to carbon, and carbon is going to take those 2 electrons. It will share them with the neighbor, technically neighbor carbon, and that neighbor carbon very soon it will give up the electrons that use to make bond with X. So now X, it will take those 2 electrons and it will leave as an X with negative charge. So what do we get? The output of this, we're going to have a double bond between the 2 carbons, and we will have also X, and X is going to have -1 charge. So we got X with -1 charge. We got an alkene. Of course, the alkene, it will be saturated and substituent, whatever they are. And plus, we have a base, and that base now is attached to hydrogen. So the base, because attached to hydrogen, is going to have a positive charge. And this reaction, we call it elimination. So let's recap whatever we said until now. We started with 2 particles and alkane, alkyl halide plus base, 2 particles. Output, we got 1, 2, 3 particles. Entire of this, reaction is happening in one step. Okay, the reaction is happening in one step, and that step is going to be the rate determining step because we have only one step, and the molecularity of that step is going to be equal to 2. That means 2 particles are involved. 1, 2, and what's the second is going to be the base. So the rate of the reaction is going to be K multiply concentration of the alkyl halide to the first, multiply concentration of the base to the first, and a unit for K, it will be molar 1 minus N to S minus 1. That's going to be M1 minus 2 multiply S minus 1, and it will be equal to M minus 1 S minus 1, which is equal to 1 over molar to second. That means we are dealing with a second order reaction. Okay. Next. So the reaction is happening in one step. Okay, and the way it's going to happen, the base, it will go after alpha carbon, the beta carbon. This is going to be the beta carbon because the alpha is here. Alpha is holding the halide. So the first carbon, I'm going to call it alpha, that it has bromide attached to it. And the second one, it will be the beta. And I want you to look for this hydrogen. Okay, now our base, the methoxide, is going to go after that hydrogen, okay, and it will try to take the hydrogen from the system. So I'm going to put the base here. Say we have ethoxide, and it has 3 lone pair, and that one is going to attack hydrogen. And now what will happen if we take hydrogen from the system? Now we will have 2 electrons there. Okay, remember, this is a sigma bond. And the sigma bond, it has such a shape. Okay. And now what will happen with those 2 electrons if we take hydrogen? Those 2 electrons, now they will be shared with the neighbor carbon. Which carbon? The alpha carbon. Okay, alpha carbon. Now let's talk about the alpha carbon. The alpha carbon, it has a sigma bond with the bromide. Which sigma bond? This is the sigma bond. Okay, a sigma bond is pointing down, so I'm going to draw this one. This is the sigma bond, and it's pointing down. Okay, next, and look, we do have a sigma star orbital in this position. Okay, so this is going to be the sigma star of technically CBr. Okay, the 2 electrons, the hydrogen is sharing with the carbons. Technically, they will go inside the sigma star of this carbon. Okay, now when they go inside the sigma star of that carbon, very soon they will carbon, kind of like reach of electron, and that carbon is going to give up the electron and it will give them to bromide. Okay, but in order to put the electron inside the sigma star, we need the dihedral angle. Okay, the dihedral angle between hydrogen and the bromide. It must be 180 degrees. Okay, dihedral angle between them must be 180 degrees. So then when the base take hydrogen from the system and leave it technically with 2 electrons, those 2 electrons, they go inside the sigma star orbital of CB, or the carbon halide. And then they will kick the halide out of the system. Okay, let me show them in the numerical projection. Okay, so the front carbon, we have a bromide at the bottom. And then the right side, we have phenyl. Left side, we have hydrogen. In the back, that I'm going to write it with red color, we have hydrogen, ethyl here on the right side, and phenyl down on the right side. Okay, so the ethyl is on the left and phenyl on the right side. Okay, and our base, the ethoxide, is going to go after this hydrogen. Where is that hydrogen? If you follow, like if you started from hydrogen and move to bromide, you will see the angle between these two is 180 degrees. Okay, so what will happen if we take the hydrogen? If we take the hydrogen, it will give up those 2 electrons, it will give them to carbon, and at the end, the front carbon is going to give up those 2 electrons to bromide. Okay, so after taking hydrogen from the system, at the same time, bromide will leave the system, and it will leave us with this. Okay, look to the yellow line that I put in there. On the right side, I have 2 phenyls. Okay, on the right side, I have 2 phenyls. So, okay, I'm gonna write phenyl and phenyl here. I wrote them on the same side. Okay, why same side? Because I can see they are on the same side. Other side, okay, I have hydrogen and ethyl. Okay, where should I put the ethyl? The ethyl is attached to the same carbon that it has a phenyl with red color. Okay, so I'm gonna put the ethyl here. Okay, I'm gonna put the ethyl here. Okay, because these 2 are connected to the same carbon. Okay, the back carbon. And where is the hydrogen? This hydrogen is connected to the same carbon that the black phenyl group is attached to it. So I'm going to put hydrogen here. Okay, now let's connect those 2 to carbon. And remember, we do have a double bond between those 2. Okay, so now I got a double bond, I got an alkene, and I have the bigger group on each side, a bigger they are pointing the same direction. And so I'm going to say the priority here, it will be for phenyl, and then that number 1, the priority on the right side, again, it will be phenyl. And those two phenyl groups are on the same side. So I'm going, and the configuration here, the conformation here, I should say like we're talking about technically about E or Z configuration, E or Z. And so I'm going to say this one, because it has the two phenyls on the same side, it will be the Z, okay, Z isomer or configuration. Okay. Now, okay. We have energy versus reaction coordinate. And we started with reactant, and we treated them with we had the alkyl halide, we added a base to it, so plus a base. Okay, the base is going to take a hydrogen from the reactant, and this is going to be our base. So I said it's going to go after hydrogen inside the transition state. And what's the transition state? The max point. That's the transition state. Inside the transition state, position of hydrogen in the leaving group must be in anti-position. Okay, an anti-position. What does it mean? It means the dihedral angle between hydrogen that will be taken by the base and the leaving group must be 180 degree. Okay, must be 180 degree. What if they are not? Then if you have a right to do rotation around the double bond, around this single bond, then rotate the molecule. The molecule will rotate and will keep rotating until we'll get these two in anti-position. Otherwise, you cannot create a double bond. Okay, so our base is going to go after this hydrogen, and very soon we will share the electron here with the neighbor carbon, the alpha carbon, and the alpha carbon it will give the electrons to bromide, and the bromide it will leave the system. Okay, so at the end you will get, as I said, you will get Z isomer plus we will get, we said ethoxide. When it gets hydrogen, it will turn to alcohol. Okay, and so I got ethoxide attached to hydrogen, and also I got the now a double bond. Okay. Okay. What will happen if the leaving group is not in anti-position? Okay, if the leaving group is not in anti-position, then what do I need to do? So let's draw. Okay, let's draw the Newman projection. The Newman projection for right now, we have bromide here, and then we have phenyl there. Okay, this is hydrogen. Okay, back we have hydrogen. What else? Ethyl is there, and phenyl is here. Okay, and now the front carbon, it will be the alpha carbon, and that one, it will be the beta. Okay, so the blue one, it will be the alpha, and the back carbon, it will be the beta. Okay, look to position of the living group. This is the living group. And where is hydrogen? The hydrogen on the beta carbon is there. Okay, I'm talking about this hydrogen. These two right now, they are in a gauge position. Why gauge position? Because the angle between the dihedral angle is 60. You cannot do elimination. Okay, so elimination, E2 elimination is not going to happen. Okay, this one will not work. Okay. Okay, so what do I need to do? Okay, in order to get some technically elimination product, we need to have rotation, and you can rotate either the back carbon or the front one. Remember, the molecule all the time will have rotation around a single bond. This is a single bond of carbon, so it can have rotation. There is nothing wrong with it. It will keep rotating around that single bond until we get the bromide in anti-position to hydrogen. Okay, so that means I'm gonna rotate the front carbon clockwise by 120 degree. Okay. So let's rotate by 120 degree. And the phenyl came down. Sorry, the bromide went down. Now you need to ask yourself, what will happen to this? This one is going to show up there. Okay. So the phenyl is going to be here. Phenyl, it will be there. And now hydrogen is going to be there. Okay. And if you decide to remove, okay, remove those, and you will get this Newman projection. So we said we have the bromide right now. Bromide is here. Okay, let me be right to the black color. Bromide is down there. Phenyl is here, and hydrogen there. Then we have we have phenyl group here. Hydrogen is there, and ethyl is here. Okay, now if you look to these two, they are in anti-position. That means the dihedral angle between them is 180 degrees. So now we can have elimination product. And anything that you see on the right side, write them and you know, like write them on one side of the alkene. So front carbon, I have hydrogen, and okay, that hydrogen will show up on the same side with the phenyl group. Okay, and next, these two, they will show up on the same side. Okay, remember, ethyl attached to a carbon that has a phenyl group. Or how about this? The black phenyl is attached. The black phenyl is attached to the same carbon that has hydrogen. So find the hydrogen. This is hydrogen. I'm going to put phenyl here, and I will connect them to the same carbon. So I'm going to say I have a carbon here that has hydrogen and phenyl group. And then we have another carbon that it has a phenyl and ethyl, okay, ethyl group. So as you see, this phenyl and ethyl showed up in the same direction. Okay, now let's attach them. And we have a double bond between them. Priority goes for phenyl, and here also for phenyl. And so this one, it will be E isomer. Okay, so you will rotate. You rotate the molecule until you will get them in anti-position. When they are in anti-position, now you can have elimination product. Okay, and next lecture, I'm going to try to practice more example and show you what will happen if we have more than one beta position. But for now, let's stop the lecture here. Thank you very much.